Hi everyone, my name is Alexey and I am glad to present our work Efficient Grouping for Keypoint Detection from Huawei Research Center, Nizhny Novgorod, Russia. This paper studies the keypoint grouping approach and how it affects the performance of neural networks. Contributions of our paper are as following. Automatic keypoint grouping approach, which help improve the convolutional neural network model in terms of training speed, inference time, and memory consumption without compromising accuracy. A powerful post-processing technique specifically designed to improve the accuracy of keypoint detection after grouping. We use recent CenterNet architecture in our work, but the same ideas can be applied to other architectures like HRNet, PostFix, and MassCRCNet. One of the first steps to overcoming the challenge in keypoint detection involves defining the model output. A straightforward approach is to concatenate keypoints from every category and deal with them separately. However, this is not the best solution because of the huge size of the model output. For instance, directly predicting 294 keypoints leads to a huge number of output channels, 901. In this case, two tensors for keypoint detection occupy 98% of the output channels and computations. It's clear that certain glowing landmarks are a subset of others, so they can be merged into one group. We view the keypoint grouping task as a clustering problem. In fully convolutional neural networks like CenterNet, the last layer produces separate channels for each keypoint type. The last layer contains weights that are applied to the same activation feature map, and it produces results for different keypoint types. We follow the intuition that similar keypoints should have convolution weights that are almost the same, and use those weights to measure the Euclidean distance between different keypoint types. To implement keypoint grouping, we use agglomerative clustering with linkage average. After keypoints are clustered, we cannot load convolution weights directly. So for each cluster, we initialize weights as mean value of weights which corresponds to the original keypoints. Additionally, we discovered that the number of channels in the convolution layers before heads significantly affects the quality of grouping approximation. We found that 32 channels provide the most efficient grouping, and we used this configuration for training. To achieve the keypoint detection task, CenterNet relies on two branches: keypoint location regression to estimate approximate keypoint locations, and keypoint heat map to refine regressed locations. Grouping approach can be applied to both. We also considered two manual groupings from papers. We discovered that decoding substantially affects accuracy of models with keypoint grouping. We introduced the heat map rescoring technique to deal with it. Here is the comparison of grouping strategies. We consider two types of grouping. Grouping with restrictions involves merging keypoints from different object classes into one group. And grouping without restrictions allows merging keypoints from the same object classes. Manual grouping from two papers are used as is. Grouping through the proposed approach is more effective than the manual grouping. This improvement is driven mostly by the effective grouping for regression head, since manual grouping has already been designed in a heat map manner. The heat map rescoring technique increases accuracy in all cases. This is particularly true when the higher accuracy gain of 6 MRP is achieved for a very small number of clusters. The best model with 120 clusters achieves slightly better accuracy compared to the naive approach, but uses less memory and works faster. Keypoint heat map rescoring technique can significantly reduce the keypoint detection accuracy drop caused by a considerably small number of keypoint regression groups. Our best grouping with 14 clusters achieves slightly better accuracy than the model with a full set of keypoints on the MS COCO human pose dataset. If we merge the close points from the same class into one cluster, they will probably be in close proximity on the heat map. Close points on the same heat map reduce accuracy. Therefore, we can change the grouping strategy and merge distant points into one group. To obtain this specified grouping, we used clusterization by referring to the negative distance between the average of sets of keypoints from the object centers from annotations. This strategy allows us to obtain models with grouping for the keypoint heat map featuring accuracy close to that of the model with a full set of keypoints. Thanks for your time, and bye!